Ozonolysis is an oxidative cleavage reaction involving an alkene. So what we do in this reaction is to use ozone, or O3, the other elemental form of oxygen, in the first step of the reaction, and then to follow it up with either zinc and hydrochloric acid or an alternative, dimethyl sulfide. So either of these could be a second step at the end. The first step is always ozone. What that does is to actually cleave the alkene bond right down the middle and replace each carbon with an oxygen. So the carbon on the left gets an O instead of the carbon on the right. The carbon on the right gets an O instead of being connected to the carbon on the left. So these two are now separate. The two carbons that were double bonded together are no longer connected at all directly. And that forms a combination of a ketone and or aldehydes functional groups, the C double bond O. Depending on the identity of the substituents here and here, it may be a combination of 2 ketones, 2 aldehydes, or 1 of each. This reaction has no regiochemistry or stereospecificity since we're not doing an addition reaction, but rather chopping that bond in half. If our alkene is acyclic, let's say, for example, that we used, in this case, it would be E3-methyl-2-hexene, and we react that with ozone, followed by dimethyl sulfide. This will be a stinky proposition, but what we do, cleave that alkene bond right down the middle into 2 fragments. We can draw each fragment separately. Now, instead of double bond to another carbon, now we add an oxygen. We'll also see the second fragment as a separate product. In this case, double bond an oxygen to that second or right-hand carbon, which now has a methyl group. Note in this case we had hydrogen here. So we get 1 ketone, carbonyl with a carbon on either side, and 1 aldehyde, carbonyl with at least 1 hydrogen attached, that's not part of a carboxylic acid or an ester functional group. Now that happens on an acyclic alkene, or one in which the alkene is not part of a ring. If we start with something like cyclopentene, we have a carbon-carbon double bond that's part of a ring. And let's just say we're using ozone. We'll use the other alternative as a secondary reagent in the second step. And again, this is a 2-step process. First step is ozone. Second step is a reducing agent, and we specifically have to separate those two. So we put the reducing agent in with the ozone. Those two will react with each other instead of reacting with our alkene. So we have to have the 1 and the 2, but you can choose either of these for the second step. When we do this, again, we're doing oxidative cleavage. That will also be a ring opening reaction because the alkene bond that's breaking was part of a ring. This can be a little trickier to draw. One approach would be to make what used to be that alkene bond just extra long. We're breaking it. We could even start as an alkene. So we'll draw the product like a really long carbon-carbon double bonds. We'll get the rest of the ring. Then we could simply erase a spot in the middle here and squeeze in a pair of oxygens. We want to be a little bit fancier. We could translate this product into a linear format. We'll notice here we have hydrogens, 1 hydrogen on each of the carbons in the alkene bond, which means that we're forming a dialdehyde product. And notice that we have carbonyls that are separated, or rather connected, by 3 carbons. 1, 2, 3. So if we want to translate this to a linear format, we can put the first aldehyde with its carbonyl carbon, and we get 1, 2, 3 carbons, then the second carbonyl. And this is a good thing to think about if you're ever given a reaction where the product is a dicarbonyl or a pair of carbonyls, and you're expected to figure out the starting material. We could look at an example of those as well. Let's leave the reagents here. And let's just imagine that our product is this ketoaldehyde. Where we have a ketone functional group on one side and aldehyde on the other, and maybe there's even some other substituent like a methyl group present over towards the aldehyde. So what we want to do to try to think backwards is to imagine that the two carbonyl carbons started out connected to each other. So we can color code them if that's helpful. We can draw them out. And we need to remember that in the starting material, they were all part of the same compound. So well, they still are part of the same compound, but in the starting material, we started with an alkene where the two carbons that are in the product, carbonyls, were in the starting material, both part of the same alkene bond. We start with the red carbon. Notice that we have a methyl group that is at the end of the ketone and not the end of the chain. So we can put that because it was on the red carbon. And then the red carbon and the blue carbon in our product are connected by a chain of 4 carbons with a second methyl group attached to the carbon adjacent, or alpha, to the blue carbonyl. So what we need to do then is add a total of 4 carbons. So we'll put those dots along in what might be something of a ring. Then we can connect those dots. And the dot closest to the blue carbon gets the methyl group. And the blue carbon, of course, also had this hydrogen, making an aldehyde. So this would be our starting material.